Thank you very much for this happy opportunity to speak to such famous scientist. Thank you very much. My theme is very complicated, so I have to choose something for today because it's not possible to speak about all aspects of this problem. I mean ontology and logic. So I have a plan for today to consider first some general questions like what is the connection between ontology, philosophical ontology and logic, and if there is a basic kind of logic which is needed or even sufficient in ontological research. I would like to propose the program of the reconstruction of logic for historically known ontologies. It's not the reconstruction of ontologies, but the logic used in ontologies. And I would like to give some examples of the reconstruction. And if it will be possible, I would like to speak something about some special problems. First, quantificational criteria of existence, multi-quantificational criteria of existence, and to tell something about ontological commitments of pure logic. If it will be possible, a few words about Platonism in physics and some conclusions. So, what is the connection between ontology and logic in general? First, I would like to remind you a well-known ontological concept of mathematical Platonism. This concept is rather well-known, and I call this kind of Platonism as explicit Platonism. However, there are also possible or present, especially in mathematical inquiries, some implicit Platonic methods or attitudes. And I think that they are most important in mathematical or even scientific practice. I think that this kind of implicit Platonism is necessary for the development of mathematics. So if we reduce all Platonic methods, it is not possible to practice mathematics at all. Well-known example, I follow Brouwer, decimal development of number pi, and of course we have and so on. And the question is quite good question. Is there a sequence like this? If somebody thinks that the question is good and there is a definite answer to the question, it means that we treat such mathematical objects as number pi as already existing and as object which has some mathematical properties which are totally independent of our knowledge, our conscious acts, and so on. So, even the use of classical logic with the law of excluded middle, double negation, and so on, is ontologically committed, is a manifestation of a kind of ontological attitude. And I think that this attitude is typically Platonic. So I think that this kind of implicit Platonism is a method of mathematical inquiry. It is the most important. Probably it is difficult to see what I mean speaking about non-verbal or implicit intellectual acts. So I have one favorite example which can demonstrate very simply and quickly what I mean. And we have well-known star polyhedron. So we can ask the question, put the question, how many vertices, edges, or surfaces are invisible on the picture? And we, without any language, any speaking, we simply perform some intellectual operations. We simply count something which is invisible on this explicit picture, and let us note that we create in our minds, in our conscious acts, an object, three-dimensional polyhedron, and in a while we supposed some suppositions concerning the symmetry of these objects and so on. Of course, these suppositions are not the only one possible, but in our culture they are typical. So it is possible to think, to operate in our intellect without any language. And from this point of view, we can speak about what we are doing after some intellectual, non-verbal operations. It's quite a good question if every intellectual operation has its counterpart in language. I think not. But it's not the problem for today. I think that from the point of view of implicit Platonism, category theory is probably the most Platonic theory. General attitude in category theory is that we simply treat some totalities of objects and consider interrelations between such objects, between categories. Of course, there are some well-known limitations, large or small categories, and so on. However, this attitude that we are face to face to something which can be inquired is probably very important. Of course, category theory enables also to study of some limitations of this kind of Platonism, but I don't want to speak today about this problem. Next question: Is logic more important than ontology in ontological research? It's a little paradoxical or deceitful question, and we can ask which kind of logic is basic, if any. I think, in general, that it is much more effective to conduct ontological research in intuitive, informal way, and only after we need to reconstruct the logic which we need to perform, to describe such intuitions. It is possible to formalize historically known ontologies together with the reconstruction of the logic which was used. And of course, the reconstructions of some ontologies historically known as Plato's ontology and theory of ideas are well known. However, they usually accept a priori discern kind of logic. I mean classical logic. For example, there are many reconstructions of Plato's theory of ideas with the application of ZFC, or even in neo-Thomistic ontology, there are efforts to describe formally theory of analogy of being also in first order fragment of ZFC, or there are trials to describe operation of separation of being in first order logic. However, I think these reconstructions are only apparent as to compare with historical sources and real aims of, for example, ancient philosophers. Thus, I think that there should be no attempt to determine a priori which system of logic is the most appropriate for ontological research. It is rather well known the thesis of first order logic as a distinguished kind of logic. And first order theories are, according to this thesis of the first order logic, are basic or even sufficient for description of mathematics, for performing research in mathematics. However, such view is not simply true. There are many reasons why it is not the true, and I will present some of them later. So at first I would like to propose a program of new reconstruction of logic for important ontologies. And for example, it is not true that classical logic is basic logic in such research. For example, when we try to reconstruct Plato's ontology, for example, in Plato's Parmenides, it appears that it's semi-intuitionistic logic without the double negation, but with the law of excluded middle. And in Plato's Parmenides, and not only in Parmenides, in Plato's philosophy, there are several kinds of negation, and it is possible to find at least 4 main types of the negation. And the basic one, the basic relation in Plato's ontology, I mean agrapha dogmata, Plato's agrapha dogmata, is intuitionistic negation. It is without the law of double negation. Also, as I mentioned before, I think that the considerations of the theory of analogy of being seems to go beyond classical logic. Also, the same concerns the relation of separation of being, which goes beyond the scopes of classical set theory and first order logic. However, there are many formal ontologies which consider this relation, however, with implicit acceptance of classical logic. Also, as it is rather well known for example, quantum logics. It is also possible to study the logic used in scientific theories and to study the relations between this logic and the type of ontology assumed. It was some general remarks, but now I would like to consider some special questions, and it is also rather well known quantificational criteria of existence, where simply what is indispensable in scientific theories is indicated by existential quantifiers. So A exists is translated as there is such X, the X is equal A. Quine's theory is monistic because everything from the point of view of this criterion exists in the same way. Simply numbers, electron, other particles, they are bound by the same kind of existential quantifier. Of course, it is also possible to consider, as nowadays many people try to do, with many different existential quantifiers, and then if such theories and logic is possible, it is possible to speak about different kinds of modes of existence. Every kind of quantifier, existential quantifier, is responsible for the indication of a discrete kind of existence. I will be back to this after. However, very popular quantificational criteria are inadequate and simply false. There are some counter examples to any kind of quantificational criteria. In Quine styles or with many different existential quantifiers, and I would like to present how one can build such universal counterexamples to all kinds of these theories. However, I would like to indicate that also pure logic, it is rather also well known, is ontologically committed, and this ontological commitment cannot be indicated exactly by Quine's criteria. For example, it is well known problem, we have three logics, and that first order logic is not pure, first order logic is not true in empty universe, so we add existential axioms to pure logic. Because of this reason, it's old and I think it's well known. Obviously, if we use first order theories, they have some specific existential axioms. For example, in ZFC, there is no need to add logical existential axiom because we have say, axiom of infinity. From this axiom, it follows that there is an empty set, and so on and so on. However, pure logic must be about something, because it's not possible to speak about nothing or about everything unspecified. One more example, I mean Frege's original logicism program. Frege usually is considered as arch-Platonic. However, his aim was to free mathematics from any ontological commitments. We know that at Frege's time, it was possible to define rational, irrational number from Dedekind's cut using only natural numbers. So Frege tried to define natural numbers as a kind purely analytical theory without any ontological commitments. However, as we know, Frege's theory is not consistent. We know what happened in Principia Mathematica. We have proofs in Frege's style without any ontological commitments. However, at same level, we have to add axiom of the existence of infinitely many individuals to prove some more advanced theorems. It is rather interesting that the reconstruction of the logic in Plato's Parmenides, there is a kind of system like this, is very close to the Frege's program because it is possible to prove the existence of infinite number of individuals assuming the existence only of one of them. However, the logic is not classical, so it's rather interesting. And also, this system of Parmenides, logic in Parmenides, is very strong because it is possible to define in this system also Leśniewski's ontology, and as is rather also well known, it is possible to define in Leśniewski's system natural numbers. Peano arithmetic theorems of Peano arithmetic and axioms of Peano arithmetics are theorems in this system. More examples of non-quantificational ontological commitments. There are plenty of them, and one can use also category theory to construct or to demonstrate such situations where we need to accept the existence of something, however, without any quantifiers. Of course, and there is one example we have in the Zariski topos. We have such formula, and one can see that there have to be some individuals, but we cannot speak about them because from this formula we cannot infer this kind of formula. So we add something more, and this leads to the construction of the Basel topos, and there we can express the above fact. As I said already, today there is an attempt to apply the theory of Quine's commitments to the resolution of the dispute between monism and pluralism in ontology. So we try to construct theories with many quantifiers. For example, one existential quantifier is responsible for the indication of abstract objects, second one for concrete objects. It is rather easy to construct such quantifiers, as many as we need, not only two of them. Of course, there are connections between many sorted logics and so on. It is rather well known, However, it is interesting that there are people which try to apply this logic to the resolution of some classical problems in ontology. I think that everybody knows what is interpretability in Tarski's sense. I would like to give a general method of the construction of counter-exams to these Quine commitments. It's the same situation with one kind of existential quantifier or with many as you wish quantifiers. And there is the concept of intuitive model. What I mean by intuitive model, maybe it's better simply we can substitute, for example, we have a line. We can substitute for every point or for some points on the line some objects like algebras, other points, set of points. And this operation I call substitution. There are, of course, many kinds of substitutions. Local, global, homogeneous, non-homogeneous, self-substitutions. Local, I mean that we have, for example, a model or a set, and we substitute a different kind of object for some or one point at this model. Global substitutions and homogeneous, for example, we substitute one kind of objects for every point, and so on and so on. And of course, it is possible to iterate this operation. I think there is a connection between the concept of structure in this, and with the use of this, I think it is also possible to demonstrate that foundations with the concept of structure are nothing new to the already known foundations. So, for example, we have Euclidean surface, and we substitute pencil of lines for every or for some points. It is also well known. We can substitute one line, and there are some interesting examples of this operation because with the use of compactness theorem and the axiom of choice, we can construct a model where the surface is disjoint sum of infinite number of lines. I think it's rather counterintuitive, so it's also a counterexample to the axiom of choice, for example. It is possible to. Of course, there is possible a general description of, for example, global substitutions. We have basic set. So with every kind of substitution, not only with the transitive models of ZFC, there is connected a band. So the substitution has a structure of topos. One more example, I use something from quantum gravity, and the author is Król. So we have in one paper, there is such kind of substitution. Every point of space-time is replaced by an algebraic structure, atomless Boolean algebra, and of course there is possible a general description of this substitution. It's a kind of global homogeneous substitution because we substitute every point by the same structure. It's the paper in Foundations of Physics, if I could remember. So substitutions are in use already. It's rather nothing new, but I think it is worth to remind this concept in the context of ontology, and especially in the context of Quine's ontological commitments. One more example, local substitution, and of course it is possible to describe substitutions in set theoretical language without any categories. So, for example, we have two copies, two transitive models of ZFC, and we try to substitute the empty set in one theory by a whole model, transitive model of ZFC. And it is possible to describe this. Of course, we have sequence of ordinals, we have infinite set. First, we need to differentiate between the names of the objects in both models. So first, we create two corresponding theories with different names of some relations, individuals, and so on. However, with the same quantifiers. It's important. There is no need to rename quantifiers. And of course, we have also, so we have renamed theories and corresponding objects in models. We have two corresponding theories, and we have to rename axioms in both theories with the above rules. It's very simply. However, it's not the end of our work, because we need to add some more axioms to speak about something interesting in this substitution. So, for example, you can add an axiom of transitivity, which secures, for example, because there are many ways to develop such theory. However, if you would like to have every set from the second theory inside empty set in the first theory, we, for example, can add such axiom. Obviously, we need to change some rules of substitutions. Now you can refer to this theory as substitutional theory, which corresponds to a substitutional model.
There are two different kinds of X and two different kinds of Y in your formula. Is that an accident, or does it mean something different?
The names are different, because I would like to combine, to speak about both theories in one theory. And such theory is not consistent without this renaming, because the empty set cannot have in the sense of the means from the first theory any elements. However, we can introduce the second relation, and now it is possible to demonstrate that such substitutional theory is consistent. So we have to decide many questions. For example, if both sets are equal in the sense of first relation of identity, or we can introduce a global relation of identity, many possibilities. However, in general, it is possible to construct such strange theory, and in this theory describing the result of substitution, there are unrestricted quantifiers. And this is counterexample to the Quine's criteria, because quantifiers cannot detect the internal structure of these objects. It is rather easy to demonstrate that both theories are interpretable in this substitutional theory. There is also the concept, there are also concept calculi which are inquired by Friedman. I mean that our formal extensional theories are intentionally undetermined. And for example, formal theory ZFC can be a kind of recipe. It's only a question of proper interpretation of the terms used. And obviously, this intentional decoration is unimportant from the point of view of formal apparatus of the extensional theory. So ZFC can speak about sets or about something which is not a set. And I think that substitutions and concept calculi demonstrate that ontological properties of objects are independent from quantifiers, because quantifiers cannot differentiate between empty set, for example, and whole model. Obviously, it is also possible to demonstrate some interesting properties of this theory, because the above example is purely syntactical. However, obviously, there are morphisms between models, and there are the functors of interpretations in the sense of Tarski. So every such theory is interpretable in their substitution. Every theory is interpreted in non-consistent theory. So this remark about consistency is essential in the concept of interpretation. How to demonstrate that the substitution is consistent? There are many possibilities also, but there is described one possibility. Of course, it's not any kind of absolute proof of consistency. They all are relative to the, for example, we need to assume the consistency of ZFC. Yeah, so I think that from the point of view of substitutions, it is more proper to use categories than sets in ontology. Simply because, first of all, we can forget about internal structure, and what about, it is possible to define the structure, the concept of structure, which was the semi of the previous lecture, because it's a kind of forgetful functor. These are different objects, set of two algebras, set of 2 points, set of 2 other objects. However, they all can be interpreted in one theory, not in ZFA with atoms. However, it is possible to build one basic theory for all such interpretations where the elements are, where the sets are composed only with atoms. And there is only first level of ZFA, so every set of something is interpretable in such basic theory. This theory is almost the same as second order arithmetic. So I think it's rather basic fact. So if we define structure as an object, if this as a set composed of atoms in this basic theory, it means that the structure is totally expressible in classical mathematics, in known to us mathematics, and I think the foundations with the use of structure cannot add too much more to the already existing mathematics. Platonism in physics, only some remarks concerning the Platonism in physics. Physics is Platonic because in physics we treat some mathematical objects as ready to use. For example, natural numbers. Of course, there are some theories, a set theoretical approach to quantum gravity, where we consider exactly in which model we use, from which model we use objects in physical theories. However, in general, physics is based on such attitude, on such Platonic attitude to mathematical objects. And the use of category theory in physics only confirm the fact. There is, at the end, I would like to put some more general questions concerning category theory and ontology. Does category theory add something more to ontology? I think that category theory cannot add nothing more to purely ontological considerations, especially concerning the mode of existence of mathematics and mathematical objects, because the objects from ontological point of view, the objects, the categories, exist in the same way as sets in set theory. And extensional tools cannot find any difference in existence of these objects. So there must exist some other tools, but not mathematical, purely philosophical, such as phenomenological, which can express and detect the fact. However, category theory falsifies many traditional ontological views, such as set-theoretic Platonism. It is the conviction that everything is a set. I think the theme is also well known to everybody, so I only mention about this. If foundations of mathematics are important, yes and no, it depends. If we are looking for the only basic object in mathematics, this conviction, I think, is simply false. However, if we are going to find interrelations between some objects from different theories, or to find something what is in common to many mathematical theories, it's the best tool to do this is category theory and categorical foundations. Also, I think category theory cannot add nothing more to epistemology. And because of the same reason as previously, because the objects of category theory are in the same way abstract or ideal as object of set theory or other structures. So I think that phenomenological consideration of the problem cannot find any difference. They are given in the same kind, in the same type of conscious acts as objects of other mathematical theories, such as objects of set theory, as sets. However, there are differences, because in a little different kind of acts, we can grasp categories and sets. There are some differences. However, these differences are not ontologically important. So I think that the best way is to use, for example, old philosophical apparatus from logical investigations of Husserl. So, some summary. I think, first of all, Quine's quantificational criteria of existence, and with many quantifiers also, are simply inadequate in ontological research. They can simply indicate what is needed in theory, however, without any ontological specification concerning the modes of existence or the difference between the modes of existence of the objects. It's not proper tool to do this. Category theory can be used in the answer of the following question. However, there is not enough time to speak more about this problem. I only indicate that it is very useful, very powerful tool, especially in formal ontology. It's unimportant. So I think, as a general conclusion, is that it is more proper and effective to use categories than sets in ontology. Thank you very much.